Okay, welcome back, grade 11s. So we are going to be doing number 15. That's where we last left off. So if you remember, this question was about the tug-of-war between Megan and Peter. Okay, when we drew that free body diagram, which was the first question on that. Let's just get this to focus. There we go. And the free body diagram for that would have looked something like this, where we had the weight of Megan, we had the normal force, okay, which is the ground on Megan. Then we had the rope, that's the tension in the string on Megan, and finally we had the surface on Megan. Okay, and the second question there was about according to Newton 3, the force which Megan exerts on Peter and Peter exerts on Megan is the same. Explain how Megan can win. Okay, from the diagram, you can see that Megan is winning. Why? Because Megan is already moving backwards. Okay, so you can see that the fact that she's moving backwards, there's definitely a resultant force acting on her. So there is a resultant force acting on Megan. Resultant force acting on Megan. The frictional force of the ground on Megan has a horizontal component. Okay, so the frictional force, I'm just going to say FF, has a horizontal component on Megan, which is greater than the force of the rope on Megan. That's very important, because remember, the force that the rope exerts on Joshua has the same magnitude as the force exerted, the force that the rope exerts on Megan is the same in magnitude as the force the rope exerts on Peter. The rope has the same tension throughout and exerts an equal force on both ends. The reason why Megan moves backwards and why Peter moves forwards is because of that horizontal component. And that's a key thing when you want to win a tug-of-war match. One must focus on pushing harder into the ground with one's legs so that the ground will push back with a maximum force. Okay, that was just some additional information that I gave you there, which you don't really have to know, but if you participate in tug-of-war, then that will become quite useful to you. Okay. The next question that we're going to do is question number 16, and 16's got the diagram. I'll just show you the diagram once again, and the question there is explain why the reading is the same in each example. Okay, so in this example, you've got a reading of 20 newtons, and in this example, you also have a reading of 20 newtons. Okay, so it doesn't matter here where the support is, whether the support on the right of the spring balanced is fixed or not. So as long as the system is not accelerating, then the spring balance will definitely be in equilibrium. So the force in the string to the left must equal to the force in the string to the right. Okay, so in other words, this spring balance here is in equilibrium because the force here and the force here are equal to each other. Okay, so if you just want to put that so that you have a written answer, you can say whether the support, so let's just put that down, whether the support on the right of the spring balance is fixed or not, so long as the system is not accelerating, then the spring balance must be in. Spring balance must be in equilibrium. That is the force in the string to the left must equal to the force in the string to the right. Okay, and then we can now move on to question number 17. It's an important question because you have a helicopter, so you have two mass pieces, okay, and so you've got the helicopter, and the helicopter is lifting two crates vertically upwards, okay, and the top crate, that means M1, has a mass of, I'm just going to put it here, 250 kilograms, and we got the lower crate which has a mass of 300 kilograms. And obviously if the helicopter is moving upwards, then these crates are also going to accelerate upwards. So the first question there is where you have to draw a force diagram of the 250 kilogram crate. So that is the crate on the top. So let's just adjust this here. So we've got our dot, okay, acting upwards, we're going to have the tension. Acting downwards, we're also going to have the tension, but let's just clarify this. Tension in upper rope, and then the tension in the lower rope. Okay, and acting downwards, you also have the weight of the crate. The weight of the crate, and you know that we know that value because it would be 250 times 9,8, and that is equal to 2450 newtons. Okay, the next question is apply Newton's second law of motion to each crate in turn to determine the tension in the lower rope. Okay, so what I would also do is I would have a free body diagram, this here, of M1, and I will also have a free body diagram here of M2, which is going to be slightly different. You're going to have your tension 2 here, so let's call that T2, T1, W, T2, and you got your weight 2 there. Okay, so I'm going to do F net. Okay, let's just get this adjusted. I'm going to do F net is equal to MA, and my net force here will be T1 minus T2 plus the weight is equal to MA. So it's going to be 8,000. You can see that value we have, minus 2450 minus T2, which we don't know, is equal to 250A. Okay, I am going to make T2 the subject of the formula. So the question is, you need to determine the tension. So if I make T2 the subject of the formula, I would get, so I'm taking T2 on that side, I would get T2 is equal to 5550, which minus 250A. Equation 1. And here I'm going to go if resultant is equal to MA again, and it's going upwards, so it's going to be T2 minus W is equal to MA. I'm going to have T2 minus 2940 is equal to 300A, and I can make T2 the subject of the formula. It's equal to 2940 minus 300A. Okay, now I can equate the two equations. 5550 minus 250A is equal to 2940 minus 300A. I solve for my acceleration, and I get acceleration to be 4.75 meters per second squared. Okay, to find my tension, I'm just going to turn to another page. To find my tension, I can substitute in either equation. So if I substitute T2 is equal to 2940 minus 300 times 4.75, you can see that I get T2 to equal 4365 newtons. So that's my tension in my lower string. So please remember, when you have this type of an example, okay, acting upwards, you'd have the one tension, but acting downwards, do not forget that you've got the tension in the string here as well as the weight of that object. Okay. And then C says, if the helicopter has a mass of 1,000 kilograms, so now the helicopter has a mass of 1,000, calculate the upward thrust of the rotor on the helicopter while accelerating the two objects. So that is not difficult again, because we're using Newton's second law again. F resultant is equal to MA, and we're going T1 minus T2 minus W is equal to MA. So it's it's just your thrust there, that's what we want, minus 8,000 minus 1,000, which is the mass of the helicopter, is equal to the mass of the helicopter multiplied by the acceleration, and that T is equal to 22,550 newtons. Okay. So we've got question number 18, 19, and 20 left to do. So let's go to question 18. And then we know we've done all the examples. For question 18, this is your scenario. So you've got this situation where you've got the mass of the ropes can be ignored. You've got two boxes, each with a mass of 5 kilograms. They're tied with a string, so obviously you're going to have tension here. They dragged across a rough surface, so we're going to get friction. Okay, and you've got a 50 Newton force. So just to let you refresh your memory, remember this 50 Newton force, which is acting at 30 degrees, is only acting on object B. It is not acting on object A. Okay, so if we had to go and solve that now, we will quickly draw in our free body diagrams for 18. And so for object A, I'm just going to draw a rough diagram. I've got the tension in the rope, which I call T1, and they told me that the friction here is twice the friction that's experienced by B. So for object B, which I just want to draw a little bit further, I've got my 50 newtons acting that way. Remember, I'm going to have my horizontal component, which I will be interested in, and I'm going to have my frictional force, and I'm going to have the tension in the rope, which is T1. Okay, so I can work out my horizontal component, which is that value there, FH is equal to F cos theta, so it's equal to 50 cos 30 degrees, and I get that to equal 43,3 newtons. Okay, so now we can see that we can now do F resultant for object A. Okay, so object A will have T1 minus twice the frictional force, we'll just call it 2F, is equal to 5 times 2. So T1 minus 2F is equal to 10. Okay, and then we go for object B. Now object B is being pulled that way, so clearly it's accelerating in that direction to the right. So when I do F resultant, or F net is equal to MA, I've got my horizontal component minus my frictional force, that's F, plus T1 is equal to the mass, which is 5, and the acceleration, which is 2. My horizontal component is 43,3 minus F minus T1 is equal to 10. Okay, now you can see that in this question I have two unknowns. Okay, so when you have two unknowns, what you can do is I'm going to make T1 the subject of the formula here, and T1 is going to equal to 10 plus 2F. Can you see that? And that's important because in this equation where I have T1, I'm going to now say that 43,3 minus F plus 2F plus 10 is equal to 10. All I did was I subbed in this for my T1. Okay, simplify further. 43,3 plus F, and if I take the 10 onto the other side, I get 0, and therefore I'm going to get my F, my frictional force. I just want to see something here. I got minus F, T minus 2F. I think I've made a mistake with my sign somewhere. It's supposed to be minus t here, so this should be minus, and so this is minus because of that minus sign there, and then this would become minus 3f. Okay, so I'm going to have 3f equal to 43,3, therefore f is equal to 43,3 divided by 3, and I'm going to get, is it 43,3? Yes, but then I also just remembered that this needs to be 10, minus 10 because of the minus sign there. So this will be 20, because if I take the 10 on the other side, it becomes 20. So as a result, I'm going to take that out. 23,3 is equal to 3f, and then f is equal to 7,77 newtons. That's only the frictional force on B, because remember I substituted there. The frictional force on A will be twice that amount. Okay, so it will be 2 times 7,77, which is equal to 15,54 newtons. Okay, so what I wanted you to realize here, it was a minus t. That's what I made a mistake with. So it will be minus 2f minus 10. Okay, and then here it would be minus 3f, and then b. So that was that. And then if I go to b asked me for the tension, so all I can do is substitute in either one. T1 minus 2f is equal to 10. T1 is equal to, minus 2 times 7,77 is equal to 10, and T1 is equal to 10 plus 15,54, which is equal to 25,54 newtons. Okay, and the last question there is, if the helicopter you needed to find C, explain why the friction acting on block B is less than the friction acting on block A. It's because of the vertical component now. So the vertical component of the 50 Newton force acting on B decreases B's effective weight, which decreases the frictional force. Okay, remember that component there, similar to the one in the tug of war. Okay, I'm just thinking whether I should just finish it, and then I know that it's done. So we've got up to number 20 to do. 2 blocks as shown in the diagram. I think I'll send that another time. Okay, so I'll put on the other 2 examples for you.